When I was in elementary school, we used to run laps around our school's playground for PE. Since it was shaped kind of like a rectangle, my friends and I would be halfway through our lap when we'd start fantasizing about hopping diagonally across the track on giant springs attached to our shoes. You could say that we were thinking out of the box, or just acknowledge that we were little and therefore inherently insane. But when we think about the things involved in that plan, especially moving diagonally, we do have to think outside of one-dimensional movement. Today we're going to be going into other dimensions, and especially looking at two-dimensional movement. Hello, fellow humans, unless you're not human, in which case I welcome you anyway, and welcome back to Fast Physics. Today we're going to be looking at two-dimensional movement and continuing to look at the elements of art. The last time we discussed art, we looked at it with one-dimensional movement. Check out that video if you haven't seen it yet. We looked at a point, which we can compare to position in physics, and we also looked at the element of line, which we can compare to displacement. Let's take a look at shape now. Shape is a pretty important element of art because it can do things that a line can't. While a line can imply space, the fact that it only exists in one dimension means that it can't actually contain any area. Just think about that example from earlier. My friends and I were running on a rectangular track. If we were to look at our movement, there would be parts where we're only moving in one dimension. After all the sides of a rectangle are lines. But when we talk about our entire path, it wouldn't just be in one dimension. Every time we turned a corner, we would be moving in a different direction. So even if our speed remained the same for the entire lap, our velocity would be constantly changing because we'd be moving in different directions on each side of the track. Let's try to graph our displacement on a position time graph, which is what we used when we were thinking in one dimension. As we headed away from our starting point on the track, which is our reference point, our displacement increases until it's the same as the length of this side of the track. We just keep adding the extra distance we cover in this direction. But as we turn the corner and start moving along this other side of the track, we can't look at our displacement in the same exact way anymore. We could set a new frame of reference at this corner of the track and start looking at our displacement from it as we move down this line, since it's from a different direction. But that wouldn't tell us our total displacement from our initial starting point. We could add those two displacements together, but that would basically just give us the distance that we traveled, not the displacement from our original starting point. That's because trying to combine vectors with different directions with all the rules of one-dimensional movement just doesn't work. We can have vectors that are in the same or opposite directions, but the very second that we start moving away from a straight line in one direction, we have to start looking at two dimensions, and that brings us back to the element of shape in art. Shape is defined as an enclosed area in two dimensions. Let's think about that definition. If you guys will remember from geometry, we find the area of a rectangle by multiplying its length by its height, which are the two dimensions that the definition mentioned. By having both length and width, we're able to have a plane instead of just a line, which lets us look at movement in different directions all on the same plane instead of making a whole bunch of different position time graphs like we were doing earlier. We can graph out the entire path that we just took on the track onto a single coordinate plane that has two dimensions. Earlier, we were only able to find our distance after traveling on two sides of the track, but now we can find our total displacement as well. That displacement is called a resultant vector because it's a combination of these two vectors. Each had its own magnitude and direction, and when we add those two vectors together, we get our resultant vector, which has its very own magnitude and direction. We're going to explore how to do that in the next videos, so remember to stay tuned. Thank you for watching this video, and be sure to check out the links in the description. This is definitely not sponsored, but Holt Physics and AP Physics Collection are both online sources, and they're both free, and I actually really like them, so I definitely recommend them to you guys if you guys are learning physics. If you guys have more resources to recommend, be sure to tell me in the comments. Bye!